All right, so hopefully now you've taken some time to look at this warm-up problem and try to figure out what do you think the answer is, right? And we're going to go over how to find it right now. And like I was saying, one technique you could do is just looking at the slope field, you might be able to visualize what the original function could look like. So earlier, we kind of showed it right here, right? If you look at this slope field, right, I know that my answer should be somewhere of the form x squared, because all of these slope fields right here kind of tell me that, oh, the graph is going to look something like a parabola. Now, I don't know where the parabola is going to be, but it's going to be something of this form, of this x squared form. The plus c is what's going to move it around, right? And that's a nice slope field for us to look at, you know. And then sometimes you can get a slope field that looks like this, and that's clearly going to be a circle. Now, my only issue is I don't really memorize an equation of a circle, but some people do, and hopefully you might remember it. It's something along the lines of like x squared plus y squared equals a constant, which is your radius, right? And whatever that constant is will tell you how big your circle should be. Now, that's all well and good. And again, here is x squared plus c, right? If I do the derivative is equal to 2x, right, and I graph the slope field, it's kind of hard to see it, but you kind of can make it out, right? It's like something like that, right? Which makes that parabola. So it's something along the lines of x squared is what the original graph is. And this is my differential equation that graphs the slope field. Looking at this problem, I just need to kind of figure out, well, I don't actually know a function that looks like this. I don't know. Do you guys know a function that looks like this one? It has like it looks like it's an asymptote here, right? And then it kind of like does this, right? And then this side does something like that. I don't actually know the function, right? I don't know the function. So that's not going to help me out. Also, even though I know the function, then I have to take the derivative of it. And then, you know, that's too much work. So what I can do instead is plug in some points and see what I get as my slope value at that point based off of these differential equations, because that's what these dy dx's represent. It's going to give you the slope at any particular point, right? And the first point I want to test out is, why not test out one of the points I circled right here, which is 6, 6, right? That's my x and that's my y value. I was going to plug this in right here. 6 plus 6, that's going to give me a slope of 12. 6 minus 6 is going to give me a slope of 0. Negative 6 plus 6 is going to give me a slope of 0. And 6 squared is 36 minus 6 is going to give me a slope of 30. So again, if you have trouble seeing what I just did right there, right, I'm taking this x value, I'm taking this y value, and I'm plugging it into these differential equations right here. So this right here was going to be 6 plus 6 to give me that 12. This right here is going to be 6 minus 6. This one's negative 6 plus 6. And this one is 6 squared minus 6. That's all I'm doing there. And I'm plugging that in to see what looks like the closest slope to this one right here. So when I'm plugging this right here, I'm looking for this slope. And what does that slope look like right there? It's a line that's going flat across like that, right? And that right there, Monica, is, you are correct. It is a slope that looks like it's a slope of 0. So that's telling me that it's not going to be A and it's not going to be D, right? Both those ones have a slope that's positive, which means that it should be going up, but it's clearly not going up in that case, right? Well, that's not good enough, right? That only tells me it's either B or C. I don't know which one it could be. So next thing I have to do is pick another point. Pick another point. I'm going to go ahead and pick another point, which I already have highlighted here, is 6, negative 6. I'm going to put this one in purple here. So in purple, let's go ahead and do that over here. 6, negative 6. I'm going to go ahead and plug in these x's and y's into our equations. I don't need to do it for all of them, right? But I'm just going to practice it just to show you guys, right? Right here, this will be 6 plus a negative 6. That's going to give me a slope of 0 at that point, which clearly that double checks it for me that A does not work. And I can go ahead and go down here and do it for C. I'm sorry, for D. I have here 6 squared minus negative 6. 36 plus 6 is going to give me 42. And again, D is also not one that's going to work because that's a positive slope. And I don't know if you guys can tell this or not. Can you guys see it right here? Can you guys tell that that is not a positive slope? That is a very negative slope. How can I tell that that's a very negative slope? Right? A very positive slope would be something like that, right? And you're saying that looks almost vertical there. But if you look closely, at the graphic, right, it's going down and to the right. It's going down and to the right. It's not going down and to the left. You see that? It's going down to the right. So that right there is telling me that there's a negative slope. So even though I got a very large number, right, I got 42. If that was a negative 42, then I would have been like, maybe that one. Maybe that one. But anyways, it doesn't even matter. A and D doesn't even fit because it didn't fit with the first point we picked, right? So let's go ahead and take a look at B and C and see which one is going to give us the right answer here. So for B, I'm going to get here 6 minus -6. 6 minus -6, right? That's how I'm going to get there when I plug that in. And that's going to come out to be positive 12. And again, it's a positive number there, which means that I should have a positive looking slope. That doesn't look like a positive looking slope. So B is actually out of the question, is not the answer, right? And we're going to go ahead and look at the last one right here. -6 plus a -6, that gives me a -12. And a -12 does look like a possible answer there because it is negative and going down. And that is probably going to be our answer since it matches for 2 points. My differential equation is going to be this one that matches up with that slope field. What do you guys think? Slope fields, it's actually one of my preferred things to look at. Slope fields are actually kind of fun. I know it sounds weird, but it's a neat thing to look at. It's one of those things like you can actually figure out which equation matches up with that one. Or you can even draw out your own slope fields. And actually, that's what you're going to have to do for some of your homework problems. They'll be giving you differential equations and asking you to draw a slope field of them. Okay? So keep that in mind. Now, you got to read these questions carefully, right? Because this one is asking which one was the differential equation that matches up with that slope field, right? Sometimes they ask it a little bit differently. They'll ask it something like this. They'll give you a slope field, and they'll ask you what was the general solution to this differential equation, which is basically a fancy way of saying what was the original equation like? Like, so let's say take a look at this one right here. At this one right here, this slope field right here, I don't know if you guys can see it. It's kind of tiny, but it's kind of like going, you know, up here, then it hits that point, then it goes down here, right? Then it hits this point, then it goes back up here, right? And then down, and so on and so forth, right? I kind of gave it away by drawing this, but see, this one's not asking you to calculate the slopes of each one, right? They're just asking you to see what you see as your original function, as your original graph right here. And I'm just drawing one particularly that's passing right through 0, 0. I don't actually know if it passes through that point or not, but I'm just drawing one just to see what this is going to look like. And some of you guys can visualize this, right? Can you picture this out? What did I just draw? What does this graph look like? It looks very familiar, doesn't it? It starts at 0, 0, it goes up to 1, and it goes down to -1, and it goes up to 1. It's the sine function, right? It's the sine function. So they have that in here, and it's actually just this one right here. And that plus c means that, you know what, if I had started here at this point instead, right, this is going to go up to this, come down to here, go up to here, go down to here, and repeat it over here, right? So this sine function works all the way up and down. Now, knowing that, do you know what the differential equation would have been? What would the dy dx equation be that created this this slope field? And don't pick one of these answers for that because I'm writing it as a dy dx. So these aren't your answers for the dy dx. What do you guys think the equation should be for this to give me that slope field? Probably one of the cosines, right? Oh, Monica's typing out b. Don't be careful. Don't type it out as just b. Type it out as like negative cosine or sine, right? Is it going to be negative cosine of x, or is it going to be positive cosine of x? Which one of these gives you this slope field right here? Anyone have any ideas? Do you think it's negative cosine or do you think it's positive cosine? What do you think? You have an idea? Negative cosine or positive cosine? That helps me. I'm going to put this one in blue. All right, that helps me calculate all of these right here. Monica's going with negative cosine. Do you have any idea, any particular reason why? I'm happy that you're coming out with an attempt here. Why negative cosine? I don't know if that's right or wrong, but looks good. It's not a bad idea. Anyone else? Do you agree with Monica? Negative cosine or positive cosine? What do you think? What do you think? dy dx of cosine of x equals to sine. We need to add a negative to the cosine. Okay. Be careful with that. The derivative of cosine is sine. You are very correct. The derivative of cosine is sine. But that's not what this problem is stating. All right? You got the right idea. I'm hoping everybody is noticing that. We're talking about derivatives of these functions, right? That's what this differential equation is. It's the derivative of a particular function. Now, here's the thing. What's the function? What's the original function in this case? The original function is not cosine. The original function is not cosine. The original function is sine. The original function is sine. And if I take the derivative of this right here with respect to x, I would end up with dy dx, which means I need to take the derivative of sine. I'm not taking the antiderivative of it. I'm taking the derivative of sine. The derivative of sine is actually cosine of x, which means my dy dx is actually this one right here. Now, that's, like I said, it's a really weird concept to look at, but check this out. Check this out. You ready for this? If I look at 0, 0, at this point right there, that's the point 0, 0, right? 0, 0. If I take that and I plug that into my differential equation, right? dy dx, right? Plugged in at 0, 0. If I plug it into cosine, cosine of 0 would be equal to 1. 1 is a positive slope. Look very closely. Do you see it? It's a positive slope right there. So at 0, 0, it has that positive slope. Whereas if I had this, and I thought it was the negative cosine, right? dy dx equals to negative cosine of 0. That's just going to come out as -1, which gives me a negative slope. So the slope field actually works out to what exactly your differential equation is. Right? You can plug in values and see what they are. But the connection that that slope field has with its original function is that when you take the integral or the antiderivative of this, we should end up at the general solution or the original solution. I like calling it the original, but they call it the general solution. But that's that. Now, if this is, hopefully it's not too bad for you, but that's all a slope field is. You need to be able to look at a graph of a slope field and kind of like, I like to just pick random points on there and plug it in and see what it is. But if they ask you a question like this, what's the general solution? You need to try to go in there and try to sketch the graph based off of the slope field. So when I look at this one right here, I try my best to sketch this graph, right? This is going to look something like that. And this is going to look something like this. If I had more over here, I can kind of sketch it over there. And I don't know what that equation is going to look like, but that's what the sketch should look like if I know that it passes through a particular point. And they're going to call that an initial condition. We'll talk about that in a second. So for this one right here, I don't know what the initial condition is, right? But I like to use 0, 0 as my first initial condition. I just try my best to sketch a graph along the way. And this one happens to look like sine. That's all it is. And, we did that earlier in the other ones like we had here. This was a quadratic, and I would be given sometimes a point of an initial condition, and then I would just sketch out my graph as best I can. And this one looks like it's going to form a parabola. Now, let me go ahead and show you something right here. There are websites that will graph a slope field for you. Now, I don't want you to do this for your homework. I just want you to take a look at this and practice with this. Let me give you this link right here. This one is a Geogebra site where if you type in you guys know that dy dx, right, is the same thing as y prime. They're just writing it as y prime right here, but you can also see it. You can type in your function right here. So let's say instead of it being cosine of y, right, we're looking at cosine of x. And there it is. You can adjust your window right here, right? Your x window is from -5 to 5 in this case. You can make it as much or small as you want on this site. So I can go from -10 to 10. Something like that. Right? And then same thing over here. I can go from -10 to 10. Right? And there's a slope field. There's a slope field. You can, now the reason why I say you shouldn't use this site is I don't know if you can tell, but each of these slopes, they're not actually at a nice point. I don't know if you can see that. See right here, this is 0, then they have a tick mark at 2, 4, 6, and 8. These slope fields right here is not actually at 1, 1, right? This right here is not 1, 1. 1, 1 would be like right there, and there isn't actually one drawn there. So just keep that in mind. If you're going to use these sites, they don't actually put it perfectly at a cross point of like whole numbers. They just do it with an algorithm that calculates it so it looks pretty. And this is what I mean. You can change the density of this thing so you can have like more or less, right? This one doesn't really help out too much, but the more dense it is, that means the more slopes you have calculated. Does that hurt your eyes to look at, by the way? Do that? So this one's okay, but if you get it really dense, you can almost picture the graph, right? You can almost picture the graph. And you can kind of picture the sine graph. Can you guys see it? It goes up to 1, and then it goes down to -1, then it goes up to 1 like a sine graph. You can also make the lengths of each one smaller, so you can actually like see a little bit like less. But then, you know, if you make it almost a dot, then you can kind of see like there's no line segment. It's just, those are just dots. Anyways, that's that one right there. Step sizes looks like it's going by 0.1. What if I wanted to go by point? And change that as well. What if I wanted by 0.1? I don't know how that works, but let's leave that alone. All right. The other part is now I wanted to talk about is initial conditions. Initial conditions is they'll say like, hey, on the slope field, the original function passes through this particular point, right? So we already seen this guy, right? And this is the function that I have. And I made an initial condition here at 0, 0, and that's going to give me this graph. If they had told me the initial condition is at 0, 4, right? If it's at 0, 4, then my graph would change, right? It would look something like this instead. It would be going up and down up here. It's still a sine function, but it just got moved up to 4, right? That's why that plus c is included there. It tells you which one of these it could possibly be, right? So once you have an initial condition, you can actually find out what that c value is. Let me show you what I mean. So check this out. Here's one particular solution, and they give you a dot here that you can move, and you can move it to whichever initial condition you want. So in this particular case, let's say the initial condition was at 0. I can't actually get 0 here because it's such a small graph, but 0, 4. Pretend that that's like at exactly 0, 4. So you can see the sine function, right, is now just up here, right? No matter where I move this, it's just me moving it along the slope field. And the function itself still looks like sine, right? Because that's what the general equation was. It was sine of x, and then we just had a plus c that we need to figure out where it is. And if it goes through this point over here, right, you still have this value over there that it has to pass through. So that's that idea there. So if you have an initial point that it passes through, you can kind of sketch what that graph should look like. And you'll have problems like that as well. Let me show you what I mean here. Let's go to another one. Let's say I had an example like this. Let me take a screenshot of this so I can get this on over here. Boop. All right, take a look at this. For your notes, I suggest you wait until this uploads onto the OneNote online, because it's probably going to be very annoying to sketch this out on your own notes. So you can go and take a screenshot of it, or take a screenshot of my notes right now, but it should be online. It should be online. So if you go ahead and look at this online, you should be able to find these notes. Okay. So let's take a look here. The graph to the right shows a slope field for the function y is equal to f of x. So understand what's being said there, right? This is the slope field for some original function y is equal to f of x. We don't know what dy dx is. We don't know what f of x is. We don't know what the function is, right? We just know that it looks like this. Second part, if the initial condition is 0, 6, what is the range of the curve solution for f of x for x is greater than or equal to 0? So before we even talk about the range, can you guys visualize what the graph should look like? What does the graph look like in your eyes when it goes through this initial condition of 0, 6? It needs to pass through this point. And I'll give you a second. You don't have to type anything out. I just want you to actually visualize. Look at this slope field and see that it has to pass through that red dot. can you kind of picture what should this graph look like? You got it in your mind? You got it in your head? Hopefully you do. It looks like this. I'm hoping you can see it. It looks like this, doesn't it? It kind of like follows through like so. And then when it gets to here, it kind of flatlines. Doesn't it? Because that slope right there, right, is horizontal. It doesn't actually go back down. At no point further down the line does it look like it bends down to a negative slope. So it kind of just flatlines right there. And that's okay. Just because it goes through that origin, right, it goes through that initial condition, that means that it doesn't actually deal with anything down here at all, right? If the original point, initial condition was, let's say, 0, 2, then that graph would look a little bit different, wouldn't it? It would look something like that. But since it doesn't go through that point, it goes through 0, 6, that's what that graph looks like. And with that drawn, I can kind of say, hey, the range for this problem, remember the range is the y value. And I'm looking for it for only from 0 and on. So from this dot and on, it looks like the range can be anywhere from 4, right, all the way up to 6, and including that 6. And you're not going to be asked the range very often, but I'm just letting you see. The bigger thing that I want you to see is understanding how to visualize your function given your slope field. Given your slope field. You guys okay with that? Hopefully. It's not too bad, right? Slope fields is one of those weird ones. I don't go into it into it too much, but it is one that is an important concept. Without slope fields, we wouldn't be able to do integrals, indefinite integrals, right? Indefinite integrals actually builds off of these slope fields. That plus c that we have to add on at the end is that idea that, like, hey, I can actually get the original function by looking at a derivative. But when I do that, I have infinitely many different graphs that I could be picking from. Right? Let me give you a couple sites though if you want to play with some slope fields. This one's the first one. This is Geogebra's version, someone coded, which is pretty nice, pretty cool. If you guys want to use that one, you can plug in your differential equation into here and then adjust your y and x windows and then play and then just look at the graph. It's kind of neat to see like what that slope field looks like. This one's a little bit cleaner to look at. Not as interactive though as being able to play with each of the slopes. Another one that I like is on Desmos. Let me get you that link as well. And I'll put this into the weekly agenda if you guys want to have it. Let me go ahead and click over here. Oh, did I not save it? That's a series and sequences. Oh, here we go, slope field generator. So this one defaults, the max points it has is from -10 to 10, right? You can code it so it has more, but here's where you get to plug in your differential equation. Right now it has x minus y, right, as the default. You can just change it to whatever function you want. We were looking at cosine of x, so let's go ahead and put cosine of x in there. And there you go. It has it right there. You can zoom in if you want. It's a little bit messier and it's like a little bit more too colorful, I'd say, for some people, but I don't know. It's up to you. What I like about this site, though, and let me give you this one. What I like about this site's version of it is they give you a point that when you move it, it calculates the slope at that point. So you see here, if I move it to 0, 0, it actually has the slope for me. Now it doesn't actually, does it tell me what the value is? It doesn't actually tell me the value, it just shows it to me. So right here at this particular point, it should be 0, right? And then at this particular point, it's going to be negative, negative, 0, positive, positive, negative. It's kind of fun to play. You can see the value of the slope as you move it around. I move it over here, move it over there, right? Gives me all the values right there, like so. Anyways, those are the ones of the slope fields. You're going to be asked to figure out what they look like and yeah, which differential equation is matching up with the slope field that's given. And then today, I'm going to show you guys how to find the original equation given a slope, given a differential equation. Okay, so let's go ahead and do that today. All right, let's go into it. Next one up, if you guys want to title your notes. That's not how you spell differ. Differential equations. Differential equations. Boom. There you go. Differential equations, right, are those things that we saw, the dy dx is equaling to a function or equaling to a derivative, and then we try to find out what the original functions were. Now, for as long as we've been doing this, I kind of just gave you these integrals, right? You've actually been solving differential equations, but it's already been set up for you. So for example, what do I mean by that? If I gave you this function, right, this is not a differential equation. Well, I guess it is a differential equation, but I've been asking you to do things like this. I've been asking you to simplify or evaluate the integral. For example, let's go with the integral of x to the third dx. You know, I've been asking you to do these problems, and you guys have been hopefully a little bit better at this, right? You don't need u substitution for this one. This one's already set up. We just use the power formula for this one, right? It's something to a power of 3. So when I do this integral, this is going to be x to the 4th divided by 4, right, plus c. And that's it. This was our answer, right? This is what we would get. Okay. So how does this relate to a differential equation? Well, here we go. You ready? I might have something like this. dy dx is equal to x cubed. Okay. And if I were to graph the slope field for this differential equation right here, y is equal to x cubed, right? Can you guys picture what the graph of what the original graph might look like? And I'm going to do that real quick. Let's go into here. Let's take a look at it on here, and let's take a look at x cubed. X cubed right here. Looks kind of ridiculous looking, right? But kind of makes sense. It's like a big U shape. Big U shape. Which kind of makes sense because when you take the integral of x cubed, we end up with x to the 4th. And if you were to graph x to the 4th, do you know what x to the 4th would look like? X to the 4th looks like that. Let's go a little bit closer. Let's go to like -4 to 4. And can you guys see that? X to the 4th, right, is a gigantic U. Right, it's like a parabola but with like a flatter bottom, right? So I'm hoping that kind of makes sense. If I graph this differential equation, I graph its slope field, it looks something like that, and that slope field kind of makes sense because, well, the original function the original function is x to the 4th, right? If y prime is x cubed, then the antiderivative of that is x to the 4th, and it's that wide-looking graph. Well, in order to solve this, right, I've kind of been giving it to you like this, but there's actually steps for solving this. And if you want to title your notes, right, the way we solve these differential equations, we use something called separating variables. It's a technique that we use, separating variables. When you separate the variables, you're basically isolating everything that has one particular variable on one side of the equation and everything else that has another variable on the other side. This is going to be looking a little bit weird because we've never actually dealt with splitting up the dy dx's, but that's essentially what I'm going to be doing here. When I separate these variables, I'm going to rewrite this as dy is equal to x cubed dx. We don't normally do that when we take derivatives, but we do this when we deal with differential equations. I know that seems like they seem like the same thing, and I agree with you. I thought they're the same thing as well, but they're a little bit different. Differential equations are a little bit different than our derivative equations when we take the derivative of it. I know, it seems like I'm just making this up, but just trust me on this one. This is how it goes. If they ask you to find the original equation or the general solution of an equation, we use this technique of separating the variables and then integrating both sides. Once you separate the variables, right, we would integrate both sides. This would become here the integral of dy. This over here will be the integral of x cubed dx. You ready for this? When I integrate both sides, the one on the right, we've already done this so many times. The integral of x cubed, right, is x to the 4th over 4 plus c. The integral on the left is new. I'm hoping that you can see that. The integral on the left is a little bit different. It's the integral of dy. I'm hoping you don't mind this, but the integral of dy, right, is just going to be y. And that's because if I do the integral of dx, I'm hoping you guys understand that, right? The integral of dx, right, it's just 1 dx is going to be equal to x. If I do it for any other variable, du, it's also going to come out as u. And the integral of 1 dy, why, that's just equal to y. Right? So you got to be mindful of your variables and your differentials. You have a dx, it comes out as x. You have a dy, it comes out as y. If you have a du, it comes out as u. Of course, though, when I did this integral of dy, it's not just y by itself. Do you guys know what else needs to come with this y? When I take the integral of a equation that's like this, you guys know what else needs to be included with that dy? Anyone have any ideas? I did the integral of x cubed dx. It wasn't just x to the 4th over 4. It was x to the 4th over 4 plus c. So the integral of dy is also going to be what? Plus c. Now this is where you got to be careful. This c is not the same as this c, meaning you cannot just cancel them out. They're different constants. So this is technically c1. I like calling this one c1. I like calling this one c2. But this gets kind of clunky, you know, because a constant and another constant, do you know what that makes if you combine two constants together? Anyone have any ideas? If I were to move this constant over here and I have here c1 minus c2, does anyone know what a constant plus a constant or a constant minus a constant would make? That's right, Monica, another constant. So what we do is when we deal with these differential equations, we just have the plus c one time. So I'd write this as y is equal to x to the 4th over 4 plus c, and that is my general solution for this differential equation, right? We've essentially gone full circle here. We spent all first semester finding derivatives of functions. Now we're going to be given derivatives, differential equations, and finding the original function. That's all we're doing here with these ones. And you'll say, Nakmi, why do I have to write through it this ridiculous way when we've already kind of practiced doing it? And that's because I've made you practice doing this first because it's a little bit easier to go this route. This right here now is showing you that what it is that you're doing when you're doing those integrals. And why I show it to you like this is because not all differential equations are going to come out looking this straightforward, like this right here. This is a nice explicit form for us to do that in antiderivative to get the original equation, right? So let's do an example. Let's do an example here, right? Let's do an example. Here we go. Let's say I was asked to solve this differential equation right here. Y prime is equal to 2x over y. Y prime is equal to 2x over y. Yeah. I'll give you guys a second to write that down. Right? Here's the thing. On the AP exam, on the free response questions, it's never just one question. It's always like 4 or 5 parts. You know, differential equations is one of those questions that they love to throw onto the free response part because they can ask roughly 3 different things from you just from this one problem alone. First question they might ask from you, given this differential equation, sketch the slope field. And that is usually about a point, but it's still a free point if you think about it. Slope fields are very simple, and they only ask you to draw anywhere from 6 to 8 points, and you just have to sketch out that slope field. You do not need to, by the way, on the free response portion, make your slope field look like this. That's way too many points that's going to be asked from you. Like I said, they're only going to ask from you like 6 points that they'll have you do. So you make sure you sketch those 6 points as neatly as possible. By the way, if you calculate your slope and you get the slope of 3, and then the next point you get the slope of 4, you don't have to make it exactly like, oh, this one needs to go up 4 and over 1. This one needs to go up 3 and over 1. make sure that this one, all you have to do is make sure is that the one that has a slope of 4 is a little steeper than your slope of 3. You know what I mean? It doesn't have to be exactly perfect. They're not gonna take a ruler and a protractor out and measure and just like, that guy's off by like a millimeter. He gets it wrong. It just has to be like, okay, he understands that this slope is positive. You show the work that it's positive, and you drew a positive slope. If you, let's say you did your work and you got a positive 3 and you drew a -3 slope, they'd mark you wrong for that. So just, you know what I mean? Just make sure you are, you understand like what it kind of should look like. It doesn't have to be perfect. Anyways, this equation right here, right? If we look at it, the slope field of 2x over y, right? If I were to graph this one, something like this. Not too bad, right? Not too bad. Make it not as dense so we can see it a little bit better. All right, it looks something like that. It looks like a hyperbola. Have you guys ever seen a hyperbola? It's like something that goes like it's a parabola, but it shoots off in both directions. The solution is going to look something like this. Whoa. There you go. See, so it has a positive one, it has a negative one, right? But it doesn't look like it opens side to side. It opens up and down. So you got this one right here, and you have this one right here. So which one is it going to be? We don't know, but we can find it. We can find it. You ready? Step 1. So after you do your slope field, that's the first part. The second part they always ask you to do was the Desmos problem from last class a hyperbola? I don't know, actually. We could try to solve it and figure it out, Monica. Actually, you know what? We should try to solve it and figure it out. I actually don't know what type of equation that is. I'll be honest with you. It could have been a hyperbola. It could have been a rational function as well. It could have been like a 1 over x problem, like a type of 1 over x problem. But yeah, it's an interesting one to do. And you could try to, do what I'm going to do right now. Step 1, when you're solving this, right? When you're trying to find the general equation, right? When you're trying to find the general equation from this, right? We just go ahead and separate the variables. Separate the variables. Now you'll say, well, knock me. I don't see any variables to separate. Remember, y prime is the same thing as dy dx. And that's what I'm going to write it in as. dy dx equals to 2x over y. dy dx is equal to 2x over y. From here, get everything that has a y on one side and get everything that has an x on the other. So I'm going to multiply the y over here. So y times dy I'm going to have on the left side. And then I'm going to multiply the dx to the other side. I'm going to end up with 2x dx. Right? I essentially just cross multiply to get them over to each other there to make sure that I have these things to work with. Next thing I'm going to do now, right? I have my dy, I have my dx's over there. I'm going to integrate both sides. The integral of y dy is equal to the integral of 2x dx. From here, let's go ahead and integrate both sides. On the left-hand side, the integral of y dy is going to be y, using the power rule, y squared over 2. Y squared over 2 equals to the integral of 2x. The antiderivative of 2x is going to be x squared over 2 times 2, which is just going to be x squared. Of course, when I do this integral from both sides, please don't forget the plus c. And you'll say, nah, don't forget the plus c on the y. I got to include it. It's part right here, right? Remember, when you combine a constant with a constant, you get another constant. Now, that's what the equation should look like. If I were to graph this right here, y squared over 2 is equal to x squared plus c. That's what my original function is. Most places, though, don't like that as your answer, especially multiple choice answers. Multiple choice answers will be y equals 2. Right? And that's what your answer choice will be looking like, y equals 2. And this is not y equals 2. We can just easily solve this, though, using our algebra skills, right? Using our algebra skills. Multiply both sides by 2, I end up with y squared is equal to 2x squared plus 2c. 2c is just a c, right? 2c or not 2c. That is not the question. Go ahead and get rid of that squared right here that's on the y as well. So I'm going to square root both sides like so. And when I square root both sides, I end up with y is equal to plus or minus the square root of 2x squared plus c. I have to include that plus c that's inside there because it's part of it before I take the square root. It actually doesn't matter where you put that plus c. Sometimes. All right. You guys okay? You guys all right? So, not okay? Feeling all right? Feeling not all right? It's a little weird. It's a little weird. But yeah. Check this out. Desmos doesn't actually, I mean, this site doesn't do it too well, but if I go to Desmos and I go to the regular graphing calculator, close this one right here, and I were to graph this original equation right here, let's say it was y squared equals to 2x squared plus a constant. Let's go with like plus 1. You guys see it? Right? It looks like this hyperbola right here. If I go with plus 5, right? That's that equation right there. If I wanted to solve it with y equals the way I plugged it in, right, it's going to be y equals to plus or minus. So we do the plus 1 first, then we do the square root of 2x squared, and plus a constant. Let's go with plus 1 just to do that. And then we go ahead and do the same equation for y equals negative square root of 2x squared plus 1 as well. There you go. That's what the original function looks like. And I just put a random value for plus c just so we can actually see it. But that plus c can change anywhere from 1 to like infinity. So if I put like 2 instead, it would look like that. You know, that's your equation. Monica asked, the ones we did last time, right? The differential equation last time, does that look like a that it was going to make a this one right here? Wait, that's the warm up. Oh, are you talking about this one, Monica? The negative x over 2y? Yeah, that's a good question. Did you guys finish this? I have it on their pair deck, I believe. Did you do all the points? Did it look like a hyperbola? That's a good one. Let's look at this problem. dy over dx is equal to negative x over 2y. If you finish that, let's take a look at this right here. This is what it should have looked like. This is what it should have looked like. I'm going to cheat. Negative x over 2y. Interesting. This thing is the solution here is actually breaking. So this thing doesn't actually do your solutions as well as you think it should. This is not what it's going to look like. But if you ignore the jagged parts, I shouldn't laugh. This guy actually coded this so much better than I did. But like I would never be able to code something like this. But there, let's just take that off and pretend you can't see it. What does that look like it's making? What's that shape? What's that shape, Monica? What does this look like? A circle. So the original equation is going to be somewhat of a form of a circle, right? So let's actually solve this one. This is a good differential for us to practice. So let's go back over here. Let's practice this one right here. Let's see if we can find the general solution for this example, right? So let's go with dy dx is equal to, crap, I already forgot what the equation was, negative x over 2y. Negative x over 2y. Okay, so let's practice that. Let's practice that. You ready? You ready? All right, here we go. Step 1, when you're dealing with these differential equations and you're asked to find the general solution, right? Finding the general solution, we're going to go ahead and separate the variables. In this particular case, it's going to separate just like the last one, isn't it? The dy's will go with the y's, and the dx will go with the x. So we have here 2y is equal to negative x dx. Integrate both sides. If you're starting to get lazy like I do, I will do it like so. And the negative sign can actually be included on the outside of this. Whoops, I forgot something. dy. Okay, that's actually important. Don't forget the dy's. That makes it the differential. So now that I have this, I'm going to go ahead and integrate both sides. I'm going to end up here with y squared is equal to negative x squared over 2 plus c. And you'll say, Nakmi, that doesn't look like a circle equation if you solve it all the way through, right? You'll end up with y is equal to plus or minus the square root of negative x squared over 2 plus c. And I agree that it's hard to see that this is one of those oval equations. It's actually easier to see from here. If you get the x's and the y's on the same side, you end up with y squared plus x squared over 2 is equal to c. I don't know if you recognize this or not, but when you have something squared plus another something squared equals to a constant, this is your circle equation. And if you divide one of those x's or y's by a number, that circle gets turned into an oval. And that's pretty much it. That's what this is going to look like right here. So that's why that one makes a circle shape. Whereas the one earlier, right, if I actually went from here and moved the x squared over, it actually would look like this. It would look like y squared over 2 minus x squared is equal to a constant. And that's the only difference between a hyperbola and a circle, is literally this sign. If you add two squares together, it makes a circle. If you subtract them, it makes a hyperbola. We don't really talk about those shapes anymore, but they're all under this thing. If you have the time to look it up, they're called conics. And you've actually learned about conics before. Conics that you mostly learn about are parabolas. So a conic is like this hourglass three-dimensional thing. And if you were to cut that hourglass with a plane, depending on how you cut into it, it makes different shapes. Normally we cut it in like at a slant like this. And most of the times the shape that we're talking about is a parabola. It doesn't cut into the bottom part of it. It just cuts into the top part. And that shape that it makes on that field that we usually play with is this parabola right here. Some of you might have been lucky and got to talk about it when it cuts in perfectly like this and it forms this perfect circle. If it cuts in at an angle from one side to the other, it forms an ellipse. And if it cuts top to bottom, that's where we get these hyperbolas. And that's all that really, that's what conics are. They're these guys right here. Ellipses, circles, hyperbolas, and parabolas. They all have these different equations that go along with them. Anyways, back to this differential equation though. Right? This is the form of a circle. That's all it is. Do you need to know that? I hate saying this. I'm just going to be straightforward. You don't need to know it to do calculus, but it helps when you're solving certain problems. I can't guarantee that they'll ask a question where like you have to specify that it is a hyperbola or it is a circle. But there will be problems where you'll be given a slope field, and if you know the equation for a hyperbola or you know the equation for a circle, you might be able to guess what the original function was based off of the slope field and based off the general shape that it makes. Am I going to force you to do that for my tests? No. Sadly, it's like a lost art now looking at conics. You probably won't be able to see any more conics until you get further in your math career. And what's going to be hilarious is that since we don't teach it in high school anymore, you might meet some old professors that are going to, if you go into the math degree, most of you are not. But if there are some of you that are, you're going to meet some professors that are old school, and they're going to be like, you didn't learn about hyperbolas? And you're going to be like, no. Like, that's a mistake. They should have taught you this in high school. We don't really teach hyperbolas anymore in high school. Actually, I'm pretty old, and I did not get taught hyperbolas in high school. Come to think of it, when I learned algebra 2, I was not taught what a hyperbola was. Huh. Yeah, but then yeah. So anyways, I'm sidetracking here. Here we go. I want you guys to practice one before I let you go today. Can you guys try this problem? Try this problem. I'm gonna give you guys. Do I have enough time for this? I don't think I have enough time for this. Yeah, no, it's fine. I want you to practice this. Try this out. I don't have much time to do the next one, but that's okay. I want you to try this. Can you guys find the the general solution for this differential equation? You ready? dy dx is equal to 4x cubed over cosine of y. So here's what I want you to do. If you don't know how to do the integral part, at least show me that you know how to separate your variables, how to get everything with y's on one side and get everything with x's on the other side. You guys go ahead and try that. Looking at this equation, right? I didn't make it too complicated. You should be able to switch those variables around. So I'll give you guys a minute. And if you guys can do that, try the next step, which is integrate both sides and see what you get. I guess right now will be a good time to talk about those of you who have decided to help your own grade and sign up in the Khan Academy classes that I have set up on your Canvas page. If you completed some of those videos or some of the assignments for the integration unit, it's unit 6 on there. It's unit 5 for us. That will help boost your last test score. If you didn't do all of them, that's perfectly fine. Some of them was something to get you going. That's going to be something that's going to help you with your grade. It's too late now to do those Khan Academies for that particular test, but it's not too late to sign up for Khan Academy for your future grades. Your future assignments are going to come from there as well. What about Calc Medic? Yeah, that too, Max, that too. That's going to be up on there as well. If you signed up for it, it will help you out grade-wise as well, but not as much as the Khan Academy stuff, because I don't think you were able to do all of them. But I'll take a look at it anyways. It depends on how much you did, Max. So if you did a lot, I'll consider it. But yeah, Calc Meta is going to go up on there as well. That's going to be our big review portion of it. Same thing with Khan Academy. Future assignments are going to be put onto there, and I'll let you guys know, of course, when I do. You do not have to wait for me, though. If you decide to go and start reviewing Unit 1, 2, 3, 4, and 5 on there, you should be able to do all of them because we've learned them all. You can go ahead and start reviewing if you want, but I am going to eventually assign them. And if I assign them and you've already done them, then that's one less thing to do. So just keep that in mind. With that being said, right, they're all going to be points that will help you towards your grade. But if you do them now, you just don't have to worry about them later. You don't have to wait for me to assign them is what I'm saying. Okay. All right. Let's keep going here. When you separated these two variables, hopefully this is what you got. You should have gotten cosine of y dy is equal to 4x cubed dx. I need to know, are you guys all right with this? I'm not losing you anywhere on here, right? I'm not losing you, hopefully, right? From here, then, we go ahead and integrate both sides. Take the integral of the left side, take the integral of the right side, and integrate. The integral of cosine of y. If you don't like y, you can think of it as x, right? It's like the cosine of x dx. What is the integral of cosine of x dx? And I'm hoping you guys will see it. It would just be sine of x, right? In this case, it will always be sine of y. The derivative of sine is cosine, right? Derivative of cosine is negative sine, but that's not the case in this case. I'm not taking the derivative of cosine. I'm taking the integral of cosine. Over here, the integral of 4x cubed is going to be x to the 4th. Don't forget the plus c. I can't stress this enough. Just doing this part where you separate the y's to one side and the x's to the other side, you get a point for that. And that's a really big deal when you're doing these AP tests. On the free response question, each free response question is worth 9 points. I know that sounds like a lot, and getting only 1 point doesn't sound like a lot. But do you know, by the way, what's the average score for a 9-point problem is? Anyone have a guess? What do you think the average score for a 9-point problem is on the AP exam? 2, yes. How'd you know? Ava, how'd you know that? Yeah, it's about a 2. It's about a 2, right? Sorry, dog just opened the door, came in. But yeah, meaning if you can separate the variables on this problem, you've earned more than about half of what the average score is. So it's a big deal, right? It's a big deal. Anyways, we'll talk more about scoring on that one, but yeah, you don't need to necessarily get a 9 on any of those questions to pass the AP exam. You can get about 2 to 3 points per question out of 9 on the free responses and still pass with a 3. maybe even a 4. We'll talk about scoring eventually, but anyways, I'm not done here. I still need to solve for y. Does anyone know how to get rid of a sine function to solve for it? By the way, free response question, I'd be happy if you got to hear. This is perfectly fine for a general solution for me. I can plug this into Desmos and I can see what the graph looks like. Does anyone have an idea though? Brian, that is correct. Inverse sine to get rid of that sign right there. So y is going to equal to the inverse sine of x to the 4th plus c. And this is probably going to be the one that shows up on the multiple choice answer choices. It'll probably look like this. The other possibility it could look like is y is equal to the arc sine of x to the 4th plus c. Which one is the correct one? And I'm just going to say yes. Both of them are correct. Both of them are correct. All right. So these are called general solutions. They're general solutions because of the plus c, right? And for any value of c, it covers all your bases, right? It covers all your bases. You can also find particular solutions. Particular solutions. When you're finding particular solutions, you're essentially solving for c. You're figuring out what that c value needs to be, and you're moving the equation to there. So let's do one example of this. I don't actually think I have enough time to finish this, but it's kind of important. Given the initial condition, y of 0 equals to 1, find the particular solution of the equation. You ready for this one? I don't think you're ready for this one. I'm not ready for this one. God, this one's ugly. Hold up. Yeah, we're going to go with it. Here's the equation. X, y, dx plus e to the negative x squared. Why do I have this problem as a problem to try? Y squared minus 1 dy. Oh, wait, there's now equal sign. Equals 0. I thought I thought I had an easier example that works into this, but I guess not. Did my mind just think like you guys would be capable of doing this? I must have. That must be the case. This looks. Maybe I'm overthinking this. Maybe I'm over stressing out for myself here. I don't know. What do you guys think? Is this going to be easier or hard to separate the x's and the y's? I need to get all the x's on one side. I need to get all the y's on the other side. How hard is this going to be? How hard is this going to be? What do you guys think? Looks difficult, doesn't it? What's the strategy that we can go up here with? Come up here with? What do you guys think? I know I need to get all the dx's and all the dy's separated from each other. So at least they're not multiplying with each other. Do you guys see that? I have a dx on this term right here. I have a dy on that term right here. I can just subtract the dx term to the other side, right? That way I can start my isolation, right? That's the idea when you're separating. You're trying to get them on opposite sides of the equal sign. So I'm going to start that way. I don't actually know if this is going to work or not. But I'm going to subtract xy dx to both sides. I end up with, on the left-hand side, e to the negative x squared times y squared minus 1. Are you guys okay if I rewrite that negative right there? That negative power bothers me a little bit. So e to the negative x squared, I'm hoping that you guys can see that. I can rewrite that as e to the x squared, but in the denominator, right? When you have a negative power, I'm just writing it into the denominator over here, just so I don't have to worry about that so much. This is going to be equal to negative x times y to the dx. It's not too bad, actually. Not too bad. It looks like I'm almost done. I just have an x term on the left side right here, and I have a y term on the right side right there. right? So I need to move those over. To move this y over, I'm just going to divide both sides by y, right? Divide this side by y and divide this side by y. And then to get the e to the x squared over, I'm just going to multiply both sides by e to the x. I'm going to basically multiply this up over here, and I'm going to divide this side down over there. Right? I'm pretty much going to cross multiply that over like so. So multiply this over here, e to the x squared. That's going to cancel out with this e to the x right there, right? So I end up with my new equation, y squared minus 1 dy over y is equal to negative x e to the x squared dx. Does it look like all my y's are on one side and all my x's are on the other side? I'm hoping that it does look like it. I think it does. I think it's okay. Right? Not too bad, not too shabby. And I think that's going to be it for today, because this is going to involve integrating both sides right here. And let me show you how to start this off. This one right here, I would rewrite this fraction just to see if I can split this up into two fractions. So this will become the integral of y squared over y minus 1 over y dy. That way I can use this property a little bit better. Y squared over y would just be y, and then 1 over y I can integrate very easily. Over here, on the other hand, this one's going to be a little bit more difficult. I'm going to take the negative sign out. This is going to be the integral of x e to the x squared dx. And for this integral, I'm going to need u substitution, and I don't have enough time to do that for today. So this right here, maybe you guys can try it on your own, practice your u substitution, because with that being said, I'm going to put up homework today for u substitution and for slope fields today. So it's 2 assignments. I know it seems like a bit, but it's not going to be too many number problems. I want you guys to start trying and practicing your u substitution, because if you look right now, to solve these differential equations, you're going to need to be very good at doing integrals. And we're going to see if we're going to see how you guys do. Aside from that, it is 10:37. I'm going to have to let you guys go. I do have office hours today from 1 to 2. If you have any questions about particular grades or these things that we've been talking about, stop by, let me know. Other than that, have a good rest of your day. Have a good weekend, and I'll see y'all on Monday. Bye, everybody. Stay out of trouble. Stay out of jail. Don't get pregnant. Goodbye. So long. Farewell.